So, last time we were looking at the algebra of real-valued function limits. And what we were using were what we knew about the algebra of limits for sequences and deducing results about algebra of limits for function limits. So we had f of x tending to L1 as x tended to a g of x tending to L2 as x tended to a in your domain D. And you wanted to check that all the things you expect happen to f of x plus g of x times g of x, modulus of f of x, constant times f of x, and they all do work, and they all work for the same reason. With the definitions we're working in, if we could have quiet, please. Otherwise, it's going to slow us down, which we really don't want, because all the hardest bits of the module are still coming up. So, as I was saying, things do work out, and we prove it using sequences and bearing in mind the relationship between convergence of sequences and function limit convergence. Because even though they're very different kinds of convergence, there's a strong connection between them. So we had our information about f and g. We took any old sequence in D that converged to A, and we noticed that because f of xn gave you a sequence of values tending to L1, and g of xn gave you a sequence of values tending to L2, then by the usual algebra limit for sequences, the sum of those two gave you a sequence tending to L1 plus L2. Real numbers, those. That's a sequence limit. But because it was true for every sequence xn in your domain D that converged to A, through values that weren't equal to A, you could turn that into a function limit. So that's the connection between them and how you can use one kind of result to prove another kind. And then you go through and you do exactly the same thing for f of x times g of x, and modulus of f of x, and constant times f of x, and f of x over g of x, as long as you're not dividing by 0. You just go through exactly the same routine, use the algebra of sequences for sequence limits, so the algebra of limits for sequence limits, and then you deduce the algebra of limits for function limits. So you should be very aware of the difference between those kinds of limits, but aware of the connections between them. And if that's unclear to you, then you really should go away and think about it. If you're happy with it, great. So now we want the sandwich theorem, and this is going to be an exercise for you, though I will draw you a picture. This is done exactly the same way. We've got a sandwich theorem for sequences of real numbers. And because you know the sandwich theorem for sequences of real numbers, if you want to try and check a sandwich theorem for function limits, you're going to convert what you're asking about into a statement about sequences, and the old sandwich theorem for sequences will come to your aid, and you'll finish it off. So here's what it says. You've got this non-empty subset of R to the D, and you've got a point that isn't isolated in D, and you've got these three functions, and I'll draw you a little picture of this in a moment in a sort of special setting. And what you're told is that the function g has values which are sandwiched between the values taken by the functions f and h. But you're also told that f of x and h of x both have limit L as you approach the point A. The same limits. That's the same A, just like in the sandwich theorem for sequences. It's the same limit. Well, the idea is that if you're sandwiched between two functions which both have the same limit as you approach A, then you have to have that limit as you approach A as well. You can't escape from doing that. So it says the proof is an exercise, but at least I can draw you a little picture of a special case. Let's suppose it's functions from R to R. And here's the value that f and h both approach. So the big one that's above everything else is h. And h of x, we're told, is tending to a as you come in. So this is, say, y equals h of x. And then there's a smaller one underneath that, which we'll call y equals f of x. But they both tend to the same limit at the point A. And G is stuck between them. Well, it seems pretty obvious that if f and h both approach the right value, L, as you approach A, then G, which is stuck between them, has to tend to the same value as well. But if you want to formalize the proof of it, you go back to the definitions, and you say, let's take a sequence in D that converges to the point A. Then you get statements about sequences, and then you get a sandwich theorem for sequences, and you get the result. But finishing off the details is an exercise for you. Right. Well, a nice corollary of that is a rather easy thing, that if you want to check whether a function tends to 0, it's enough to check that the modulus tends to 0, and conversely. Actually, this is a combination of the previous two results. The algebra of limits tells you that if the function values tend to something, then the modulus of the function values will tend to the modulus of it. So if the functions tend to 0, then the modulus of the function values will tend to modulus of 0, which is 0. So one way round is the algebra of limits. The other way round is sandwich theorem, because the function is sandwiched between minus its modulus and plus its modulus. So if the modulus tends to 0, the function has to tend to 0 as well. But it's sort of pretty obvious anyway. So, the reverse implication, that's from the algebra of limits. Since the modulus of 0 is 0. And the forward implication is from the sandwich theorem, because minus mod f of x is less than or equal to f of x is less than or equal to plus mod f of x. So if modulus f of x tends to 0, then minus mod f of x does as well. That's part of the algebra of limits. You're multiplying by minus 1. So you get it squeezed on both sides by its modulus. And if they both tend to 0, then f of x has to tend to 0 as well. So if you're trying to check something tends to 0, you might as well estimate its modulus and prove that that tends to 0, which again often involves using the algebra of limits, as we're going to do in the next problem. So our task with the next example is to prove that the limit as xy tends to 0, 0 of x cubed y to the 4th over x to the 6th plus y to the 6th is 0. And this is, I would say, a non-trivial task, because if you come in along the x-axis, it's 0. If you come in along the y-axis, it's 0. You can check straight lines coming in. You can check a few curves coming in. But it doesn't matter how many particular ways of checking, of coming in like that you check. If you check any number of specific approaches, like x equals y squared, y equals x squared, all sorts of curves like that, that's not enough. You've got to show that all methods of approach are okay. But fortunately, we've got the sandwich theorem to help us. And what we're going to do is we're going to estimate the modulus of this using a case-by-case analysis. And this is probably one of the most sophisticated arguments we've used so far. So we'll set f of xy equal x cubed y to the fourth over x to the sixth plus y to the sixth and remember we only have to consider x, y which are not both 0. We don't have to, we're not even allowed to consider the point 0, 0, which is good because you'd be divided by 0. But you're supposed to look at what happens as x and y approaches to 0, 0 through values aren't actually at 0, 0, because that's what limit means. The function limit ignores the value at the point you're approaching, even if there is one. In this case, it's not even defined. So what we'll do is we're going to estimate the modulus of f of xy using case-by-case analysis, and then we'll use the sandwich theorem. So we're going to estimate okay, let's try that again. We estimate the modulus of f of xy for xy not at the origin using case-by-case analysis. And then we're going to use the sandwich theorem. Now, this is going to be a relatively easy case-by-case analysis. There are lots of situations where you have to do something slightly more sophisticated, but the basic idea is often the same. So let xy in R squared with xy not at the origin. And we're going to consider two cases. Case 1, case 1 is going to be where mod x is less than or equal to mod y. In this case, since it's not at the origin, y can't be 0. We don't know if it's positive or negative, but if y was 0, then mod y would be 0, mod x would be 0, they'd both be 0, but we're assuming we're not at the origin, so that doesn't happen. Right. Okay, so then we're going to estimate things quite easily. We want to look at the top, modulus of x cubed y to the fourth. That's equal to mod x cubed mod y to the fourth. But mod x is less than mod y, so that's smaller or equal to mod y cubed mod y to the fourth equals mod y to the seventh. Now, if I want an upper bound for how big f is, then I need a lower bound for the denominator, not an upper bound. So that's an estimate. That's how big can the numerator be I want to know how small can the denominator be. So the denominator, I want to know how big modulus of x to the sixth plus y to the sixth, how small that could be. Well, that's equal to mod x to the sixth plus mod y to the sixth, because everything's positive. And that's greater or equal to mod y to the sixth. Notice that that's greater than 0. So, in this case, the modulus of f of xy, which is equal to modulus of x cubed y to the fourth over the modulus of x to the sixth plus y to the sixth, we know the numerator is less than or equal to mod y to the seventh, and the denominator is greater or equal to mod y to the sixth. So that's smaller or equal to mod y to the seventh over mod y to the sixth equals mod y. So in case 1, modulus of f of xy is less than or equal to mod y, which is a nice easy estimate. Let's have a look at what happens in case 2. If case 1 doesn't hold, we must have case 2, which is mod x is greater than mod y. But in this case, x is not 0. Also, we just need to use mod x greater than mod y. You could use greater than if you want. If you want to use a strictly greater, you can, but greater equal will do for the next. I'll sacrifice a bit of information just for the sake of symmetry in the argument. Mod x cubed y to the fourth, again, it's mod x cubed mod y to the fourth. This time, it's smaller or equal to mod x to the seventh, because mod y is less than or equal to mod x. And modulus of x to the sixth plus y to the sixth, which is again mod x to the sixth plus mod y to the sixth. But this time we note that that's greater or equal to mod x to the sixth, which, as we know, is greater than 0. So you're not dividing by 0 here. From this, in case 2, modulus of f of xy is at most, again, the numerator we know, oh, well, okay, sorry, let me write that. It's equal to modulus of x cubed y to the fourth over modulus of x to the sixth plus y to the sixth. And that's, this time, that's less than or equal to, well, the numerator we know is less than or equal to mod x to the seventh this time. And the denominator is greater or equal to mod x to the sixth, so we could use that. And you get x. Modulus of x. A common mistake, by the way, is to say that the numerator is less than or equal to something at this point and use that. But remember, you're dividing, the denominator. Sometimes people say that the denominator is less than or equal to something and divide by that, but that would be a mistake because we're dividing by it, we want to say that the denominator is greater or equal to something, so that you can divide by it, and then your result will be less than or equal to something. Well, so in one case it's at most mod y, in the other case it's at most mod x. But in both cases it's less than or equal to, say, mod x plus mod y. in both cases, and that covers all possibilities, so this inequality for all xy not equal to the origin, you've got a sandwich. You've got 0 less or equal to modulus of f of xy is less or equal to mod x plus mod y, which tends to 0 plus 0 equals 0 by the algebra of limits. As xy tends to 0, tends to the origin. So you've got a sandwich, 0 on the left, something tending to 0 on the right. You've established an inequality for all points away from the origin, so you can forget about what f actually is. This sandwich is enough to show that f of xy tends to 0 as xy approaches the origin. So by the sandwich theorem, modulus of f of xy tends to 0 as xy tends to 0, 0. And remember, if the modulus does it, so does the function. And we finished. Any questions about that argument? It's certainly one of the trickier arguments we've seen so far, because you had to do a case-by-case analysis and then say, having done the case-by-case analysis, a certain inequality was true for all xy not at the origin. With no questions about that, we'll move on to the next part. Anyone need more time on those slides? Okay. Right. Now for some routine stuff about new continuous functions from old. Again, we'll use sequences to help here, because we've got this very useful characterization of continuity in terms of sequences. This is really very light, and we've also got the algebra of limits for function limits, which we could use as well. So there's lots of different ways we can do these ones. And the idea is to show various ways that you combine continuous functions and you end up with more continuous functions. It's a completely standard approach that you did all the time in calculus anyway last year. So I'm going to assume that you've got two different functions, f and g, defined on some domain, taking values in the real numbers. Both of them are continuous at some particular point, not yet assuming that they're continuous anywhere else. And we just take some constant as well. And here are some more functions that are also continuous. You can add the functions together and you get another continuous function. You can multiply the function f by a constant and you get another continuous function. You can multiply the functions pointwise. That's not the composite function. That's the pointwise multiplication. So remember that fg here, if you want to know what it does to a point x, it's f of x times g of x, not f of g of x, which is got a different notation. And mod f, remember, is another function where you just take its value at x is modulus of f of x. But again, we've got algebra of limits results already, so it's not at all surprising that you get that these things have got the right limits. if A is not isolated, you could just use the algebra of limits results to prove this immediately. If A is isolated, then in fact, continuity is automatic. So let me comment that if A is not an isolated point, of D, then you can just use the algebra of limits for function limits. For example, limit x tends to A of f of x plus g of x will be f of A plus g of A because limit x tends to A of f of x equals f of A. That's the continuity of f. That's f is continuous at A. Remember, that's my abbreviation. CTS is the abbreviation for continuous. And limit x tends to A of g of x is equal to g of A because g is continuous at A. So then you just get everything, and you do the other ones the same way as well, again, using the algebra of limits for function limits. If A is isolated, well, then all real value functions on D are continuous at A anyway, so there's nothing to prove. You can check that bit. So that does it. I'm leaving the remaining bits for you to do, just as I left the remaining bits of the algebra of limits for you to do. So you get new continuous functions from old, in all the obvious ways. Any questions about these ways of combining continuous functions? An immediate corollary then, continuous means you're continuous at every point. So you just substitute in the previous result and say at every point, and you get this one, that if you add two continuous functions together, you're continuous. If you multiply a continuous function by a constant, it's going to be continuous. Point-wise product of two continuous functions is continuous. Take the modulus of every value taken by a continuous real-valued function, and you'll be continuous. And you can divide continuous functions as long as you're not divided by 0. So this is immediate for the previous result. So you can use that to combine all sorts of continuous functions to make new continuous functions in exactly the sort of way you'd have done in calculus and said, oh, we can tell that's continuous because it's made up of continuous bits. And we now know quite a lot about that. Now, you can also prove all those using sequences, and in at least one of the years recently, I can't remember which, I did give a sequence proof of that result. So you can go through, do it using sequences instead. For composition of continuous functions, I think I always use sequences, though you could also do it with epsilon and delta. But you can't really use the algebra of limits when it comes to composition of functions. So here's composition of functions. Just for ease of the statement, I'm going to assume that the function f is defined on the whole of r to the d, taking values in r to the l, and g is defined on the whole of r to the l and taking values in r to the k. This means there's no problem defining g of f of x, because any value taken by f will be somewhere in r to the l, and then you can take g of f of x safely. If you don't do that, then you need to make sure that wherever f is taking values, g has to be defined there. So if you want to do composite functions, you need to make sure that if you're going to do g of f of x has to make sense, so f of x has to be somewhere that g is defined. So then you form this composite function, g composed of f, which of course goes from r to the d to r to the k. Well, let's just draw you a little diagram there. So you've got r to the d being mapped into r to the l using f, and then that's being mapped into r to the k using g. And so if you take a value in r to the d, take f of it, you're then in r to the l, and then take g of that, and you end up in r to the k, which is why the composite function takes you from r to the d into r to the k. And now we've got to prove, we're assuming that f and g are continuous. I want to prove the composite function is continuous, and I'll do it with sequences. The sequence definition of continuity, so here's an optional. Recall, we need to show that whenever a is in r to the d and xn is in r to the d converging to a, then the composite function should do the right thing. It should tend to f of g, f composed with g of a, as n tends to infinity. Or in other words, we need f of g of xn, because that's what the composite function does. Oh, sorry, I've got f composed with g and g composed with f the wrong way around. Silly me. In this one, it's g composed with f. It's g composed with f. That's g of f of xn. That's a sequence of values, and it should tend to g of f of a as n tends to infinity. So to prove that, it's let and suppose time. So let a be in r to the d, and suppose you could also do a let. Suppose you've got a sequence in r to the d which converges to a. Well, we know that f is continuous. Since f is continuous from r to the d to r to the l, we know that the f of the limit is equal to the limit of the f values. In other words, f of xn will tend to f of a in R to the L as n tends to infinity. But now we can apply the fact that G is continuous. This is a sequence in R to the L converging to a point in R to the L, and G is continuous on R to the L. So since G is continuous, which I'll abbreviate to CTS, from R to the L to R to the K, you can apply G to that convergent sequence. G of f of xn will tend to G of f of a as n tends to infinity. I'll put that back in terms of the composite functions. In other words, G of f of xn tends to G, silly me, here we go again, G composed of f of xn tends to G composed of f of a as n tends to infinity. But that's true for every sequence xn converging to a point A in R to the D. So that shows that G composed of f is continuous. And we finished. Using sequences is a very clean way to develop theory of continuous functions. It's just unfortunate that it's a bit harder to see whether functions are continuous or not using sequences. And I think that the real way to think about continuity is to use epsilon and delta. Any questions about that proof? Now, you can do the same thing point by point, but as I said before, you've got to be careful your domains and codomains and everything match up. So if f is continuous at A and G is continuous at f of A, then being a bit careful, because you can only define G composed of f if f of x is in the domain of G, then G composed of f will be continuous at the point A as well. And I'll leave that to you as an exercise. So the problems in general when G of f of x is not defined. Because you've no reason to believe in general that f of x is going to be in the domain of G. So you have to do a bit of thinking about when does that work and when doesn't it. But as long as everything's defined near the points or you know what your domains and codomains are, you can make this work point by point as well. So that brings us on to epsilon and delta. Now, epsilon and delta is really what analysis is all about. You haven't really got to grips with analysis unless you can work with epsilon and delta, and you know the difference between for all epsilon there exists a delta, and for all delta there exists epsilon, and there exists delta for all epsilon. If you need to be able to know the difference between which order you put your quantifiers in and which quantifiers you're using, and get to grips with exactly what it really means for your functions. So here's something that was probably from ACF last year, though you may have seen it in calculus as well. What does it mean for a function defined on the real line to have a limit L as you approach this point A in terms of epsilon and delta, it came out as the following. For every positive real number epsilon, there should be a corresponding positive real number delta. And as you change epsilon, you'll probably have to change delta too. Delta is almost a function of epsilon here. So that for every real number x, if it's close enough to A, the function value will be close enough to L, expressed by if the modulus of x minus A is strictly between naught and delta, because you're not supposed to check the value at the point, it may not even be defined. But if you're close enough to A but not equal to it, then the function value should be close to L. If you make epsilon smaller, you probably need to make delta smaller. But every time somebody re-chooses epsilon for you, you're allowed to choose a different delta depending on that epsilon, as long as you know that no matter which epsilon somebody chooses, you can choose a delta that works for that epsilon. That's the meaning of this: for all epsilon there exists a delta. You don't expect to get there is a delta that works for all epsilon. That would mean if there was a delta that worked for all epsilon, that would be a very powerful statement that says that for a particular delta, you were incredibly close to this value, but sort of in fact, it would tell you that you were exactly equal to L for all values nearby. But I'll leave you to think about that. If you swap the for every epsilon and there is a delta, if you swap those around, you get a completely different statement. Then you want to know how do you do continuity using epsilon and delta. This is very similar, except that the limit value has to be f of a. So this time the function must be defined at a. The limit value must be f of a this time. And you don't need the naught less than mod x minus a less than delta, because if x equals a, you get it for free. If x is equal to a, then the modulus of f of x minus f of a is 0, which is definitely going to be less than epsilon. So this one says that if x is close enough to a, then f of x will be close enough to f of a. In a very carefully expressed way, for every epsilon, there is a delta. If somebody gives you a smaller epsilon, then you'll probably have to re-choose delta. And sometimes the delta that works will be epsilon. And sometimes the delta that works will be epsilon over 2. And sometimes the delta that works will be epsilon squared. Sometimes delta has to be much smaller than epsilon to make this work. If you're working with the square root function, which is nicely continuous, and you want to know how close do you need to be to the origin to get the value smaller than epsilon, then you need to take delta to be epsilon squared. So for something like that, which is very steep at the origin, then you're going to have to take a very, very small delta compared to epsilon. So what happens in D dimensions and L dimensions? Well, you get exactly the same pair of propositions. I won't prove them because the proofs are the same as the proofs that you've got from last year. But in case you're a bit fuzzy on those proofs from last year, I suggest you go through, look at those proofs from last year, translate them into the language from this year, and make sure that these two claims I've got here are true. So what do we have in terms of epsilon and delta? What does it mean to say that the limit as x tends to a of f of x is q? The answer is that for every epsilon greater than naught, there should be a positive real number delta, depending on epsilon. If somebody gives you a smaller epsilon, you're going to have to re-choose your delta. But nevertheless, you know that whatever epsilon they choose, you will be able to find a delta that works. That's if it's continuous. That's if it's got this limit. And again, it was if you're close enough to a, the function value should be close enough to q. Only this time it's done with norms because they're vectors. So if x is close enough to a but not equal to it, so the norm of x minus a is strictly between naught and delta, then the function value should be close to q. the norm of f of x minus q is less than epsilon. And for continuity, it's the same again. F is continuous at the point A. That says, again, you don't need the naught less than norm x minus a, because if x equals a, then you know that f of x equals f of a, and you get the norm of f of x minus f of a is 0. That's guaranteed to be less than epsilon here. So you get that bit for free, so you can forget the naught less than, and you only have to look at norm x minus a being less than delta should imply that the norm of f of x minus f of a is less than epsilon. All these different notions of function, limit, continuity, whatever, they all express somehow that if you approach the point A, then the function values will approach the limiting value, whether it's L or f of a or whatever. And they're all formalized in some way, using sequences or using epsilon and delta. The nice thing about epsilon and delta is you can actually draw pictures, and you probably saw some pictures last year, to sort of say, what does it mean to say that this condition holds? How can you tell that this condition has failed for this function? I'm not going to go through drawing all those pictures again, but you can draw for yourself pictures for specific functions and try and decide for yourself, why do they satisfy this condition? And this is a condition that you can really get to grips with. If you draw a nice function, a nice sketch of a continuous function, then you can really see about how close do you have to be to get the function values to be that close in the y-axis. But as I say, I'm not going to go through all that again. You can check that these things work, but I am going to try and work with epsilon and delta a little bit. And what we're going to do next time is we'll use epsilon and delta to prove this rather useful lemma, which comes in quite often in analysis. But we'll stop there today.